In this video, we'll determine whether a series converges absolutely, converges conditionally, or diverges. A series is called absolutely convergent if the series of absolute values is convergent. For example, the sum from 1 to infinity of -1 to the n minus 1 over n squared has absolute value terms 1 over n squared. So if we consider the series that goes from 1 to infinity of 1 over n squared, this is a convergent p-series. Converges by the p-series test. Therefore, we can say that our original series is absolutely convergent. A series is called conditionally convergent if it is convergent, but it's not absolutely convergent. In other words, it converges, but the absolute value of its terms form a series that do not converge. In this example, if we look at the absolute value of each term, then we have the series from 1 to infinity of 1 over n. This is the harmonic series which diverges. Diverges by the integral test. So we cannot say that our series is absolutely convergent. However, the original series may still converge. It's an alternating series, so let's apply the alternating series test. The limit as n approaches infinity of 1 over n is 0. So we satisfy the first criteria for the alternating series test. And our next term, 1 over n plus 1, is strictly less than our nth term, 1 over n. So we satisfy both of those criteria. Therefore, our original series converges by the alternating series test. So our original series converges, but the series formed by the absolute value of its terms does not. Therefore, we say that our original series is conditionally convergent. The absolute convergence theorem tells us that if a series is absolutely convergent, then it is convergent. To prove this, let's assume that we have a series made up of the absolute value of terms and that it converges. If it converges, then it has a finite sum. So 2 times that sum is also finite, and therefore 2 times the series of the absolute value of a sub n must also converge. If a sub n is a positive term, then when we add a sub n and the absolute value of a sub n, the most it can equal, well, it will equal 2 times the absolute value of a sub n. If a sub n is a negative term, when we add a sub n to the absolute value of a sub n, we get 0. So the sum of a sub n plus the absolute value of a sub n must be between 0 and twice the absolute value of a sub n for all n. And since this forms a finite sum and 0 is a finite value, then anything in between must also have a finite value. So the sum made up of a sub n plus the absolute value of a sub n converges by the direct comparison test. Now the series from 1 to infinity of a sub n is equivalent to the series of a sub n plus the absolute value of a sub n minus the series of absolute value of a sub n. Since we've already shown that this sum is finite, and our assumption is that this sum is finite, the series of their differences must converge. In this example, we'll determine whether the series is convergent or divergent and classify any convergent series as absolutely or conditionally convergent. We could start with an alternating series test to see if this converges, but then we're going to have to, as a second step, take the absolute value and test that. It would be more efficient to test the absolute value first, because if we find that the absolute value converges, then we don't need to test the original series. We can conclude that it converges. So we'll save ourselves some work by testing the absolute value first. If it happens to diverge, then yes, we will still have to go back and test the original series. So the absolute value would be the series from 1 to infinity of 1 over 3 to the n. This is equivalent to the series from 1 over infinity of 1/3 to the n, which is a convergent geometric series. And since the absolute value converges, then the original series converges. Is absolutely convergent. For our next example, we have an alternating series, but before we jump straight to the alternating series test, let's check for absolute convergence. The absolute value of each term would be n factorial over 2 to the n. So let's consider that series as n goes from 1 to infinity. The limit of the nth term as n approaches infinity is not 0. Factorials grow faster than exponentials, and so this limit is not 0, and therefore our series diverges by the nth term test. If the absolute value diverges, that doesn't necessarily tell us anything about our original alternating series, so we should perform the alternating series test on the original series. But the first step in the alternating series test is to find this limit and verify that it is 0. Since it is not, we know that the original series is also divergent. So in this case, neither the absolute value of the terms nor the original series converge. They are both divergent. In our final example, we consider the alternating series -1 to the power n over the square root of n. Let's test for absolute convergence first. The absolute value of our terms will be 1 over square root of n. And we can rewrite this in the form 1 over n to the power 1/2. This is a p-series where p equals 1/2, and since p is less than 1, this is a divergent p-series. So our original series is not absolutely convergent. The absolute value diverges, but we still have to check to see whether or not the alternating series converges. So let's apply the alternating series test. The limit as n approaches infinity of 1 over square root of n is 0. And now we compare the n plus first term, which would be 1 over square root of n plus 1, to the nth term, 1 over square root of n. The square root of n plus 1 is larger than the square root of n, so this fraction overall has a smaller value. And because we meet both of the criteria for convergence, then we can say that our original alternating series is conditionally convergent. In this video, we've seen what it means for a series to be absolutely convergent, what it means for a series to be conditionally convergent, and we've looked at the absolute convergence theorem, which tells us if a series is absolutely convergent, then it is convergent.